So, the next topic is the change of curvilinear coordinates, change of curvilinear coordinates. These parameters u1, u2 of the surface are also called curvilinear coordinates. So, the idea in this title is that if you have a coordinate system u1, u2 on a surface and you are changing it to a new coordinate system u1 dash, u2 dash, dash I will put in the left side, okay, so that there is no confusion with the derivative. So, suppose a new coordinates are chosen u1 dash, u2 dash, then what will be the relationship between different type of quantities on the surface. For example, what happens to Gijs, what happens to the area, what happens to scalar product, things like that, what happened to the tangent vector and its component when you change from one coordinates to another coordinate. So, this is the kind of thing that we will be discussing now. So, suppose you are going from u1 to u1 dash, u2 dash, then and where these u1 dash and u2 dash, they are differentiable functions of u1, u2. So, u1 dash is a function of u1 and u2, and this is its differentiable function, and similarly u2 dash is also a differentiable function of u1 and u2. Okay. So, with this understanding and u1 dash, u2 dash, they are independent variables, and u1 dash, u2 dash are independent variables. Okay. They are independent variables, they are differentiable function of u1, u2. So, this means the Jacobian delta u1 upon delta u1 dash, delta u1 upon delta u2 dash, delta u2 upon delta u1 dash, delta u2 upon delta u2 dash. This determinant is non-zero. This is in short notation is also written as del of u1 u2 with respect to delta u1 dash u2 dash. This is the short notation for the Jacobian of the transformation. So, we assume from the beginning that this is non-zero. So, if I have a tangent vector say r, so r is the position vector, r is the position vector of a point on the surface. So, the vector r, suppose even in R2, if you have this vector and here is the coordinate frame of R2. So, now what we are doing, we are changing the coordinates. So, first of all we have coordinate x and y along x axis and along y axis. So, there are two ways you can choose some other coordinates. Suppose I choose this, a new plane, same plane, but coordinates are coming from this line and this line. So, I have rotated. There are other ways also. You can translate, you can choose differentiable functions, say polar coordinates, which are not obtained by rotation, which are obtained in different way. So, you are going from one coordinates to another coordinates. What is important to note down that this vector, if you look at this vector, this will remain the same whatever coordinates you choose. So, vector in itself will remain the same. What will change? Only the components of the vector with respect to the new coordinates. So, if this is the vector, then if you look at this vector, this will be same when you will consider is as a function of u 1 dash u 2 dash. About vector, you know that vector, as long as its direction and magnitude is same, it is same for us, is it right? So, vector will not change, it will remain the same. All right. Now, there are certain convention, we have to fix it up. R I means the derivative of r with respect to u I. Okay. These are certain notation, and now you can think of r I dash also, and that means del r upon del u I dash. This is what I mean. R is a function of u 1 u 2, r is also a function of u 1 dash u 2 dash. So, you can differentiate r with respect to u I as well as you can differentiate with respect to u I dash as well. So, these are certain notation that you need to keep in mind. Okay. Now, let us see what is the relationship between r I dash and r I first. So, r I dash, as I told you, is del r over dash, is del r over del u I dash. This I will rewrite as del r upon del u I into del u I upon del u I dash, or okay, you can call it j. Okay. So, this will be r j into delta u j upon delta u I dash. This is the relationship between r I dash and r j. Okay. So, this is the first relation that we have. We will note down it somewhere. I will keep all my relations over here. So, r I dash is equal to r j or r k if you wish, r k del u k upon del u dash I. So, this is number 1. Okay. Now, I can look at g I j's. What happens to g I j's? So, g dash I j means the derivative of r dash I, dot product of r dash I with r dash j. Okay. R dash I we know what it is. This is equal to r k into del u k upon del u dash I. Okay. Dot. Similarly, I can write down the relation. It will be some r L del u L upon del u dash what? J. So, the right side, these two are vectors. So, their dot product is g k L del u k upon del u dash I del u L upon del u dash j. So, this is the relationship between g dash I j and g I j. So, this is the relation number 2, this is first, and the second is g dash I j is equal to g k L into del u k upon del u dash I del u L upon del u dash j. This is box 2. Okay. Now, we move on to some other quantities. G upper ij's are also the quantities. So, we will see how do they transform. So, this is the transformation of G I j. This is the transformation of G I j. This was the transformation of R i's, transformation of the tangent vector R I. Now, next I am talking about transformation of G upper I j. So, you may call these as the laws of transformation. Okay. If you look at these laws of transformation, the first and the second one, what you notice is here the quantity in dash system, here the quantity is non-dash system. So, when you go from dash to non-dash, in the derivative the dashes are down. Same thing happening over here also. When you go from dash to non-dash, the dash in the derivative is coming down. So, this is how we remember what is the law of transformation. In fact, this is the way we distinguish between quantities. There are quantities whose law of transformation will be different in the sense that you go from dash to non-dash, the dash will come up, here they are coming down. For example, G upper I j's, its law of transformation will be diagonally opposite to the law of transformation of G lower I j. So, we know that no, this is tensorial, this is tensorial, because these when you look at these the matrix G with component, you can distinguish it with tensorial quantities, because there are quantities like vectors, but there are quantities which are linear maps. So, linear map and the vector linear dual of a linear map is also a vector space of the same dimension, you can identify them, but the elements inside the dual space and the original vector space are different. Indifferent in what sense? In the tensor, as a tensor quantity. Okay, so, these are tensor quantities, and what is the difference? The law of transformation is difference. Okay. So, we know that the G upper I j and G lower I j are related like this: G dash I j into G lower j k dash. Okay. If I look at these two, their product must be a Kronecker delta. Which Kronecker delta? I k. Okay. Now, I will make use of this defining relation to work out the law of transformation. So, G dash I j. So, this implies that G dash I j multiplied by G dash j k, G dash lower j k transform like this. So, this I can write down G j k. So, L m I will write down here del u m upon del u dash j, no L first, del u m now upon del u dash k. This is Kronecker delta I k. Here del dash is not important. Kronecker delta will remain the same thing whether wherever you write. Okay. Okay. Now, I can do over here. Okay. Now, what I will do, I will multiply it by g dash. So, multiplying by delta u. Okay, here itself. Okay, let me multiply by del u k, del u dash k upon choose some index. Let us choose L m, next is m. So, these are short notation which I will be using. The meaning is that I am multiplying the above expression by this quantity. So, what will happen? G dash I j into G lower L m del u L upon del u dash j. Now, this quantity is del u m upon del u dash k, and you are multiplying by this quantity. So, let me multiply it by del u dash k upon del u n. This will become del u m upon del u n, and that is nothing but Kronecker delta m n, because in a coordinate system they are independent coordinates. When you take derivative of one coordinate with respect to another, derivative will be 0 unless the two variables are same. So, the answer will be Kronecker delta m n. So, I will put Kronecker delta m n, and the right side will be Kronecker delta I k multiplied by del u dash k upon del u n. Now, what Kronecker delta will do? This will change m into n, because m is a dummy index. So, m is a dummy index. So, this taken sum over m. So, when m become n, its value will become 1, otherwise its value will be 0. So, this n m will change into n. So, the left side will become it is visible. Okay. So, g dash I j into, now m I will change into n, g l n into del u l upon del u dash j. Okay. And the right side same thing happening, k is a dummy index. So, it will change into n. So, this will become del u dash k is gone. So, k will change into this del u dash I, sorry, it will change, it will I upon del u. Okay. Okay. This is fine. Now, the next I will multiply by, now I have to bring g n and some more into the right side. So, multiplying by g n p. So, the my next operation is multiplying by g upper n p. I will leave g dash I j over here, and I will try to finish all these quantities from the left, and will bring automatically some quantities will emerge in the right. So, my next step is to multiply by g upper n p. So, this will give me g dash I j okay, as it is into g lower L n. Now, it is being multiplied by g n p, and the other quantity is del u L upon del u dash j, and the right side will be g n p multiplied by del u dash I upon del u n. Now, look at the left side first. These two matrices are inverse of each other, okay? And n becomes a dummy index. So, it becomes G dash I j, and this will become Kronecker delta P L, okay, into del u L upon del u dash j, and the right side is okay as it is, G n p into del u dash I upon del u n. Okay. Now, once again this Kronecker delta change L into P, then you will take the sum, because L is a dummy index, you will take sum over L. So, whenever L will become P, it will be 1, otherwise it is 0. So, this L will turn into P. So, G dash I j multiplied by del u P upon del u dash j equal to G n p del u dash I upon del u n. Now, you want to remove this term. What will you do in order to remove this term? So, this term will be removed if I multiply it by some del u dash, some q upon del u p. Okay. So, p you want here also. So, that is why I will multiply by del u q upon del u p dash. Okay. N is already there, you want p. So, p will come when you have. Okay. So, what will happen after this multiplication? This will remain G dash I j del u p upon del u dash j into del u dash q upon del u p, and the right side is G n p into del u dash I upon del u n into del u dash q upon del u p. Okay. Now, look at these two terms. You have del u p upon del u dash j into del u dash q upon del u p. So, that becomes G dash I j multiplied by Kronecker delta q and j. Dash does not make any difference, okay. And the right side you keep as it is. You are not going to make any change over here. Now, look at the left side. This Kronecker delta will change j into q. So, I can write down this as G dash I q, and the right side is G n p into del u dash I upon del u n into del u dash q upon del u p. I and q have come over here, and these n and p are the dummy indices which you can choose according to your wish. And now, you can see, if you look at this law of transformation, so yes, dashes are coming up. When you go from dash system to non dash system, the dashes are coming up, whereas for G lower ij's, dashes were coming down. So, I can write down the third rule of transformation as G dash I q is equal to G n p into del u dash I upon del u n into del u dash q upon del u this is the law of transformation for G upper ij. Okay. So, what you see more closely, what are those indices which are fixed or free, and what are the dummy indices. So, the free indices are I and Q, they are coming over here also. Okay. So, these same indices will be there, whereas N and P are dummy, you can choose their name according to your convenience. Okay. Now, come to law of transformation for an arbitrary tangent vector. Transformation of tangent vector, not basic, general. Yes, transformation of a tangent vector. Transformation of a tangent vector. So, let us consider a tangent vector A. So, suppose A is a tangent vector which with respect to u1 u2 coordinates can be written as some ai ri as a linear combination of basic tangent vector, and the same tangent vector can be written as some other say a dash j into r dash j. Now, r dash j we know how does it transform. So, the right side will be written as a dash j, r dash j, how will you write down? I here, and this is dummy. So, it will be dummy means r k del u k, and in the denominator you have del u dash j. Okay. I would prefer to write r k over here, no problem. Okay. One thing more I will be doing, look here, I is a dummy index over here. So, I can change the name of a dummy index. So, you can make this also as k, okay, or you can make this I, does not matter. So, the left hand side I will rewrite down as a k r k. Okay. Now, I will bring the right side into the left side and take r k common. So, the above expression will be written as a k minus a dash j into del u k upon del u dash j multiplied by vector r k equal to 0. Now, a linear combination of r k is 0. R k's are linearly independent, they are two vectors r 1 and r 2. This is the linear combination of the two vectors. So, this scalar must be 0. So, this implies a k minus this equal to 0. This is equivalent to saying that it is a dash j del u k upon del u dash j. Okay. So, this is the law of transformation, but you have written in the opposite way. So, you can convert it when you are going from non dashes to dashes. So, non dashes come up. So, or I can rewrite down this as a dash j equal to, you can revert the matrix, its determinant is non-zero, we have assumed. So, you can revert the matrix. So, this is equal to a k into del u dash j upon del u. Okay. So, this I can write down as a fourth law. So, number 4 is a dash j is equal to a k del u dash j upon del u. number 4. Okay. Now, if you look at number 3 and number 4, you will say they have the same law of transformation. Dashes are up when you go from dash to non-dash, dashes are up. Here also when you go from dash system to non-dash, dashes are up, whereas these two quantities dashes are down. So, these are similar quantities, these two are similar quantities tensorially. And now, I can address some other questions like what happens to scalar product, what happens to area when you go from one coordinate system to another coordinate system. So, this is the next thing. So, first of all, invariance of the inner product or scalar product. So, invariance of a scalar product. Invariance of a scalar product. Okay, under the change of coordinate transformation. So, suppose A and B are two tangent vectors and their dot product is A dot B, scalar product or dot product. So, let A and B be two tangent vectors, be two tangent vectors on a surface, of course. Then I will write down A as then A dot B. A dot B will be equal to some G I j. This you have computed earlier also. A you will write down A I R I, B you will write down as B j R j. The dot product will be G I j into A I B j. We have done several times this product. So, we know A I are the components of A, B i's are the component of B. So, this is understood. Now, this will be equal to, now you want to write down G I j in terms of dash system. So, when you go from dash to non-dash, when you go from here to here, okay. So, what will happen? Just the reverse, you can do it there also. So, this will be G, you can write down K L if you wish, G K L, and this will be del u dash I up dash I upon del u k into del u dash j upon del u l. I am reading relation number 2. I am just revert dash okay, into A I B j. Okay, into A I A dash I will write down. Okay, A dash A I we have found the rule. Yeah? Now, first you write down, now these are scalar quantities, these are scalar quantities. So, how do we, did we discuss? Yes, here, yes, yes. So, it will be, okay. So, if I write like this means I am already assuming that it is same as A dot B is same as A dash dot B dash. That means I am already assuming it that it remains the same, but that I need to prove. Okay, so, this is not the right approach. So, what should I do? A dash ओके ये पॉज कर दीजिए थोड़ा, उसके बाद हम इस पर गौर करते हैं. So, this can be written as G I j, and now look at the transformation of A I and B j. So, we can revert this transformation in number 4. So, if you look at number 4, I can go from A k to A dash j. So, I need A I. So, this can be rewritten as A dash j equal to A I del u dash j upon del u I. Okay, and this gives me A I equal to A dash j into del u I upon del u dash j. So, A I is written like this. It will be, I can choose the index instead of j, I can choose k, because this is dummy index. We can write down the name according to our convenience. So, A I is A dash k del u I over del u dash k. Similarly, if you want to write expression for B, so if this is B, this is also B. So, I is now j. So, I can write down this as j, this also as j, and change the name of dummy index, say L and L. So, B j is B dash L into del u j upon del u dash L. So, this becomes G I j into del u I upon del u dash k del u j upon del u dash L multiplied by A dash k into B dash L. Now, if you read this much and look at the law of transformation for G lower I j, transformation number 2. So, it becomes G dash k L. So, this is G dash k L into A dash k into B dash L. Now, this is nothing but the dot product of A and B in the coordinates. This is A dot B in the coordinates u1 dash u2 dash, and the left hand side was the dot product in coordinates u1 u2. So, what you observe at the end, that the dot product or the scalar product of two vector remains invariant when you go from one coordinates to another coordinates. So, this is the conclusion. The scalar product remains invariant when we change coordinates from u1 u2 to u1 dash u2 dash. Yes, under any coordinate transformation, the dot product will not change, it will remain the same. Okay. Now, next is the transformation area. Before area, I have to tell something more. After doing the invariance of the tangent vector, now let us consider GIJs. So, the law of transformation number 2. So, we know that G dash I j is equal to G k L into del u k upon del u dash I del u L upon del u dash j. This is the law of transformation. So, what you do? You take determinant in both sides, taking determinant in both sides, because all of them are matrices, taking determinant in both sides, of course. So, this will become G dash I j determinant, and this determinant of the product equal to product of the determinant. So, this is G k L into determinant del u k upon del u dash I into del u L upon del u dash j. Okay. So, this I can write down determinant of G dash I j G dash, and this I can write down as G. Now, look at this. What is this? This is the matrix. This is the matrix del u 1 upon del u 1 dash del u 2 upon del u 1 dash del u 1 upon del u 2 dash del u 2 upon del u 2 dash. This is the determinant, and similarly this is the same determinant. So, in fact, we can write down this as del u 1 u 2 upon del of u 1 dash u 2 dash, okay. And this is the square. So, this 2 is nothing but the square of this determinant. Okay. So, if you look at the transformation of G, when you go from G dash to G, the component will be related like this. So, this is the transformation law for G. This is the law of transformation. This is the law of transformation for G. G means the determinant of G I j store. Okay. I can talk about the invariance of the area element. So, if suppose the area of a region is a dash under coordinate transformation u 1 dash. So, this will be equal to G dash into d u 1 dash d u 2 dash. This is how the area we compute in the coordinates in u 1 dash u 2 dash. Okay. Now, G dash we know what it is. G dash we have just computed. So, under root means under root G, and then you have to take under root and the square will go off. It will become del u 1 del u u 2 upon del u 1 dash u 2 dash, and you have then d u 1 d u 2, okay, because these do not matter. So, you see what is this? This is same as the area A. So, whether you compute the area in u 1 dash u 2 coordinate system or in u 1 dash u 2 dash, it remains the same. Okay. This area, why this area is same? Because we know that in the advanced calculus course, you know, when you compute the integral from in one coordinates and you go into another, you always multiply by the Jacobian. So, that area is the same. So, I have used here a theorem of advanced calculus. Then when you compute area in one coordinates and you go into another, this is how it is related. Okay. So, I stop at this point and we will continue in our next lecture with the second fundamental form. That third unit will start.